Settle in, you guys. Get your notebooks out. We got some stuff we got to do, and this might be a little longer, so I apologize in advance, but not really too much, so sorry. All right, here's what we need to talk about. We're talking about gas behavior. So far, we just did some like rudimentary stuff from Chem 1, but now we got to kind of talk about some more details of this. So first of all, when we looked at PV equals nRT, this is the ideal gas law. Well, the ideal gas law is simply that. It represents an ideal gas. So what we didn't talk about is what does it mean to be an ideal gas? So an ideal gas is something that meets the criteria for the kinetic molecular theory. KMT, kinetic molecular theory. And basically what the kinetic molecular theory is a set of assumptions that we're going to make about gases to let us do all that math. So here are some examples of some of those assumptions that we might make. First, we assume that gas molecules are negligibly small. They take up no space in comparison to the whole volume of the gas, because if you magic school bus yourself inside, there would be huge amounts of empty space and then gas molecules spread out. So in terms of the whole space that they take up, the gas molecule itself, it's not important. Another thing that the kinetic molecular theory assumes is that gases are in constant random motion. They're moving. There's no set path. Nothing is affecting that path. It is totally random. A third thing that we could assume is that there are no intermolecular forces or attractions, which we really haven't spent any time yet this year, but you may recall hydrogen bonding or London dispersion forces, or just dipole-dipole attractions. It assumes that there are no attractions between them because they're moving fast and they're far apart from each other, which also contributes to the fact that the collisions between them are perfectly elastic. In other words, they bounce back exactly because there's nothing attracting them. And then another assumption that we make that lets us do all this math is that the average kinetic energy, put that line over the top term for average kinetic energy of the gas molecules, is proportion to the Kelvin temperature. And we'll look at some of the math that you saw in 5.6 to kind of make heads or tails of what that means, and this certainly is part of it. So these set of assumptions all allow us to use things like the ideal gas law and assume that what we calculate will actually be right. And it turns out that in real gases, sometimes this might not turn out to be right. So before we get into the math, I want to just mention, when is a gas not ideal? In other words, when does it not really meet those assumptions? And that's going to be true under situations where you either have very low temperatures and/or, doesn't have to be both, very high pressures. And think about this. If the temperature is really, really low, that gas could get close to condensing. If it gets close to condensing, that means there will be attractions between them. It means that the gases won't be in constant random motion because they're slowing down. So that's not going to be holding true. If we take a look at really high pressures, under really high pressures, the way you put a pressure on a gas is you end up actually decreasing the volume of the container, and you push the gas molecules really close together. Well, if you do that, once again, you're going to affect this, because now you get the molecules close together and they might actually be attracted to each other. You're also going to affect this. If your container starts getting too small because you're putting so much pressure on it, the size of the molecule in the context, for example, if I get this so small that the gas molecules actually start to occupy space in relation to the size of the container, it's possible that this one will stop holding true. So just informationally, I want you to know that there actually is a corrected version of the ideal gas law. And here's what it looks like. Just copy it down. I'm not going, or don't copy it down. I honestly don't care, but I just want you to see the corrected version of it. The corrected version is known as the van der Waals equation. And I am not going to ever ask you to actually use this. But I want you to see it, because here's what it does. It's still P times V equals nRT, but what it does is it puts a correction factor in it for when we have, let me label this here, these guys, which is what we would consider to be a real gas, one that does not meet the criteria for the kinetic molecular theory. So it puts these corrections, for example, in here, pressure depends on how many moles of gas you have, it depends on the volume of the container, and it depends upon this constant that relates to the intermolecular forces found between them. And then volume, if you get volume really small, could be impacted by how many molecules, but it also has a factor that relates to molecular size. Again, you will not have to calculate anything with this. I just want you to realize that when we get to places where there is a real gas, there are ways to calculate it, and there is this corrected version that exists. All right, here's what I want to do. A lot of what you read in 5.6 is this really complicated equation deriving stuff, and I'm not so concerned that you can do the math as much as you can understand what some of the equations are for. So we're going to look at some of the concepts behind the equations and what those concepts are telling us about the behavior of gases. So here I'm going to jot down two of the equations that are given in your book. One is this. And here's the other. And I want to talk about what they mean, not how to plug numbers into them. So we're going to look at this very first one here. And this is E sub T, or translational energy, which really for us, for our purposes, is a form of kinetic energy, the energy of movement. And this is talking about the energy of movement for our gas molecules. So here's what we can learn from this statement. Kinetic energy is directly related to temperature. So kinetic energy is proportional to temperature, which is one of the tenets of the kinetic molecular theory. If temperature goes up, the kinetic energy goes up. N sub A, this is Avogadro's number. 6.02 times 10 to the 23rd. Great. But here's what I want you to notice. Nowhere in here does it care what the molar mass of the gas is or anything. So in other words, kinetic energy, it doesn't matter what the identity of your gas is. It just simply matters what the temperature is. That's what I really want you to get out of that equation. R, of course, is the gas law, 3/2, great, constant. All right, let's look at the second equation that's given. This is really going to tell us what things influence pressure. So let's take a look at that, and when we peek at it, N refers to, let's use a different color, N refers to the number of molecules. M refers to the mass of the molecules. This little crazy U thing is really speed. Might even want to replace it with a V. Might make your life a little simpler. It's the speed of the molecules. V is the volume of the container. So what can you get from that? Well, pressure. What things influence pressure? How many molecules are in the container? The more molecules, the more pressure. The mass of those molecules. Really, the mass of the molecules combined with its speed. If you have molecules that are traveling at the same speed, but one is heavier than the other, it's going to have more of an impact on pressure. That's what that's referring to. Pressure also depends on the volume of the container, and notice it's an inverse relationship. If it's a big volume of the container, it's going to have an opposite impact on pressure, less pressure. If it's a small container, it's going to have a bigger impact on pressure. Turns out that if you actually put these two together, you can, and because we know things like PV equals nRT, we know that that's true. Might be a little fun exercise, you know, if you're bored one day this weekend. You can actually manipulate those together in order to prove this thing you know before, that energy is equal to 1/2 mv squared. And this is really kinetic energy is 1/2 mv squared, which you've learned in physics, and that, you know, energy is related to both mass and speed. Those are great things to know. So again, not so concerned that you can plug in numbers there, but that you understand what the basic premise is of what that means. All right, next thing. I want us to look at something known as a Maxwell-Boltzmann distribution, related to what we've just been talking about. And the Maxwell-Boltzmann distribution are really a specific kind of graph. And so I'm going to give you two examples of this kind of graph. They both have a very similar shape. This first one is number of molecules on the y-axis and molecular speed on the x. Actually, they're both going to have those labels, but we're going to be looking at different things in them. So again, this one will also be number of molecules versus speed. Okay, the first one, we are going to look at a given sample of hydrogen gas. But we're going to look at it at 3 different temperatures. So let's say that this represents what this graph would look like if this was being taken place at 100 Kelvin, as an example. So when we look at this, it looks like the vast majority of molecules at 100 Kelvin have this kind of speed in here. There's more molecules at that speed than perhaps at these speeds. Okay, if we were to change the temperature, the graph changes. So if we were to take the same sample of gas at 300 Kelvin, the graph starts to spread out. And if we took that same sample of gas and spread it out even further, say 700 Kelvin, notice that the graph doesn't just completely shift over, but in fact it spreads out over the course of this change in temperature. But at 300 Kelvin, again, the vast majority of molecules now have a slightly higher speed, and at 700 Kelvin, the average speed increases. But here's what I want you to see. Notice that at all temperatures, we still have some slow molecules. And think about that. If the molecules are hitting each other, and at the moment of collision, how fast is it going? It's not moving at that moment of collision. And then it's got to speed back up into its normal speed again. So we will always find slow molecules. And that's what contributes to this graph spreading out instead of just simply shifting over. So this is one thing that we can see. Notice that kinetic energy, which is proportional to temperature, is 1/2 mv squared. So if our kinetic energy is increasing because the temperature is increasing, then we would expect to see a relationship, how that relates to speed. Now, all of them in this example have the same mass, so mass is not influencing it because it's hydrogen gas. Now let's look at the second graph. In the second graph here, let's assume that this entire graph is taking place at 25 degrees Celsius. The whole thing. And let's say we have 3 different samples of gas. Let's say that this represents, notice very same shape, that's on purpose, a sample of chlorine gas. Let's say that this represents a sample of nitrogen gas. And then this represents a sample of helium gas. Same amount in each sample. So let's say, it's a mole of that or whatever. But chlorine gas has a molar mass of 71 grams per mole approximately. Nitrogen has a molar mass of about 28 grams per mole. And helium, 4 grams per mole. And so what you can see from this is that the heavier molecule has a average speed that's lower than the medium-sized molecule, which has an average speed that is lower than the very small molecule. So the small molecule has the has the greatest average speed, which again, if we look at this equation here, now the kinetic energy stays the same for all of them because the temperature is at 25 degrees. But here, the mass changes. And if you have the same kinetic energy but a small mass, you're going to have a high velocity or a high speed. If you have a large mass, like the case of chlorine, you're going to have a smaller speed. And so this Maxwell-Boltzmann distribution is a way to show once again and really illustrates how here we still have slow molecules. I don't care how big that molecule is. It's still going to have some slow ones, but we're going to have kind of, again, this spreading out where more molecules of a variety of speeds, but yet the average speed, or the speed of most of the molecules, is generally higher with the smaller molecule than with the others. All right, we're doing good. We're almost done. All right, drawing on my screen here. Last thing I want to bring up, and again, this is related to some of that heavy math that's in 5.6, but I'm not concerned with the math, with you plugging it in, as much, but I am concerned with you understand what the premise is. So let's just take a look at the math concepts again and peek at some of the other equations given in this particular section. One of those equations, I think it's the main equation actually that we're going to focus on. We'll just focus on this one equation. It's called URMS, really fancy name, 3RT over MM. So this is given in there. They use U for V, so it's a velocity, and this stands for root means, whoa, go away. Root means squared velocity. So here's what that means to us. That is average molecular speed. So they found this mathematical relationship for average molecular speed. 3 is in there. This is the gas law constant. It's actually the 8.314 joules per mole Kelvin version. That's so that the units work out. Temperature is in Kelvin. This is molar mass. But it's defined that the molar mass has to be in kilograms per mole. And if you're like a unit lover, a little side note is that a joule is a kilogram meter squared per second squared. So, if you plug that in, you can see why this had to be in kilograms per mole. Turns out, if you actually do all the units with this meters squared per second squared and you end up taking the square root of it, you would end up with an answer for average molecular speed in meters per second. So by all means, play with the units and figure that out. But let's just take a look at what that means for us. Here's what you should be able to glean from that. The average speed of a molecule is directly proportional to temperature. We saw that up here in this one. The average speed of a molecule is directly proportional to temperature. As you raise the temperature, the average speed goes up. Well, this is just the mathematical way of showing what we saw in that first graph. Another thing, average molecular speed is inversely related to its molar mass. Again, this is just the mathematical equation that proves what we saw. Whoa, go away. It proves what we saw here. that as the molar mass changes, it's inversely related to its speed. Small molar mass, high speed. Big molar mass, low speed. That's what we saw. This is just the mathematical equation. Am I concerned that you can plug numbers in? I am not. Am I concerned with the concept? Yes, I am. Here are some other things that could correlate then as a result of knowing that. That if I took the same gas at two different temperatures, then the gas at the higher temperature generally moves faster on average. That's just saying in words what we saw in the graph, what we see in that equation. Again, in words, if we have at the same temperature two different gases, so now their kinetic energies are the same, then the more massive one, the bigger one, right, is slower, or the smaller one is faster. That's what that equation tells us for that kind of thing. So all of that is going to help us to answer this question. Why does a helium balloon deflate faster than an air-filled balloon? You've all seen it, you guys, right? You know, you get that balloon, you're so excited, you're a little kid, you have this little helium-filled balloon, it's floating in your bedroom, and then mom and dad tell you have to go to bed, and then in the morning you wake up and it's like on the floor and so sad, and you're sad, right? Yeah, we've all been there. Okay, and if you haven't, yay you. So you have this helium balloon, or if you compare it to an air-filled balloon, which of course is not going to float, I'm just drawing it this way, but of course it's on the floor. But in the morning, your air-filled balloon, which is, you know, right, mostly nitrogen, that's what the air is. Even when you blow it up, you're still breathing out the nitrogen you breathed in and didn't use. All right, yeah, there's a little carbon dioxide in there, even a little oxygen, but whatever. It's not sad in the morning. It's still the same size, but sometimes the helium balloon, it's actually littler. It deflates faster. So now the question is why? And so we need to understand the process of effusion, which is the movement of gas molecules through small openings. In other words, the helium balloon effuses faster than the air-filled balloon effuses. So this one effuses slower. Because in a balloon, if you magic school bust yourself inside, there would be little tiny openings that the helium atoms eventually make their way out of. And same thing in the air balloon, little tiny openings that, you know, the nitrogen molecules can manage to get through as time passes. Well, its ability to get through an opening is totally about its molar mass. There's actually a little equation. I'm going to give this to you. This stands for the rate of effusion. And this is an equation that shows, if you kind of peek through what this means, that the rate of effusion is inversely proportional to its molar mass. So let's just show that with what we have. So the rate of effusion of helium over the rate of effusion of nitrogen is equal to, we flip these, notice how they're opposite. The molar mass of hydrogen is 28 grams per mole, and for helium it's 4 grams per mole, which is the square root of 7. So I don't know what that is. So the square root of 7, which is somewhere between 2 and 3, 2 point something, that means that helium will effuse 2 point something times faster than nitrogen. And based on what we talked about, that makes sense. The helium molecules are going to fit through the openings more easily. They're more likely, if they hit an opening, to go through because they're smaller. And so as a result, and if we even go back to this, kinetic energy, we're talking about the same temperature here. So kinetic energy isn't changing, but if they are smaller, they must be moving faster. So if they're moving around faster in there, they're more likely to encounter an opening than something that was bigger. And so it shouldn't be surprising that a smaller molecule will effuse faster because it's moving faster and more likely to encounter an opening than something that is a bigger molecule that is effusing slower. So that kind of wraps us up. That is a ton of stuff. I hope you took good notes on that. Again, I'm much more with all this mathematics stuff concerned with, do you understand the concept behind it? Less concerned and not concerned that you can literally plug numbers into that. So, all right, we will see you guys on Monday.